So this is Chapter 6 called Astronomical Instruments. We'll mostly be talking about telescopes here. However, other astronomical instruments are cameras and spectrographs, also known as diffraction gratings or prisms, the things that separate light into its component wavelengths or frequencies. So we'll talk about all of that a little bit. So here's a picture of the Hubble Space Telescope. The Hubble Space Telescope is, I think it's conceded to be the most important instrument, single scientific instrument in the history of mankind. It's responsible for more discoveries than any other single instrument. It orbits at about 350 miles, I think, maybe 370 miles above the Earth. It has a mirror that's about 8 feet in diameter, 2.4 meters in diameter. It has been operating for about 30 years, and so it's taken a ton of data. It can operate 24 hours a day. It can look at a single object for days at a time, collecting data. So it's a very important instrument. It's going to get replaced by the James Webb instrument. That's been imminent for a long time. But the James Webb Telescope has been built, and it's going to go in a slightly different area of space. It's going to actually orbit the sun. So that's the Hubble. Here's a picture, 3 pictures, all of the same thing. All of these pictures are of the Orion constellation, and the one on the left is in the visible spectrum. This is something you might see through a telescope or a pair of binoculars. The one in the middle is taken in the X-ray wavelengths, and the one on the right is taken in the infrared. This is just to emphasize that we sort of need to be able to look at things in other wavelengths besides visible if we want to get as much information as possible out of the light that astronomical objects are sending to us. Here are some early astronomical instruments. This is some Incan ruins from the 15th century, and on the right is Stonehenge, which was made in 3000 to 2000 BCE, so 4,000 or 5,000 years ago. Ancient civilizations all over the world built things to help them observe the skies and look for the solstices and the equinoxes and things like that, to keep calendars. So this was not uncommon. So let me switch over to the text here. So this is section 6, Astronomical Instruments. I don't know why I wrote gathering there. Astronomical Instruments. So some of the vocabulary is angular resolution, light gathering power, adaptive optics, CCDs, which are charge-coupled devices. A CCD is the thing inside your cell phone that the image gets projected onto by the camera, so that it's the thing that grabs the image when you take a picture. Eyepiece, focus, interferometer or interferometry, reflecting and refracting telescopes, objective lens or mirror, Schmidt-Cassegrain telescope. These are just some of the words, so sort of the important ones I stuck in there. There might be some more as we go through. So the basic optical instruments if you want to be an astronomer, you need 3 things typically. You need a telescope, you need a spectrograph, the kind of thing that breaks the light up into its constituent components, the colors for visible light, and you need a camera, so that you can store whatever information it is you're using. So if we talk about telescopes, there are 2 main functions and optical components of a telescope. The main functions are light gathering power and focusing the light to a point or an image. So the 2 main components are an objective mirror or lens and an eyepiece. You typically have 2 sets of glass. One is the piece that's at the end of the telescope that you're not looking through, and the one is the piece that you are looking through. The piece that you are looking through is the eyepiece. The other piece is called the objective. It's called the objective because it's the part of the telescope that receives the light from the object. So typically, light is focused by the eyepiece, but sometimes it's focused by the objective. Some telescopes don't have eyepieces. So the main properties describe. Let me fix that. The main properties of a telescope. The first one is light gathering power. One of the primary functions of a telescope is to gather as much light as possible, because that's how you get a really crisp image. This is either done with a mirror in the case of a reflecting telescope, or a lens in the case of a refracting telescope. We'll come back to that in a minute. But the area of a mirror, since they're just circles, is pi r squared. That's the formula for the area of a circle. In the example I give here, if mirror A has a radius of 1 meter and mirror B has a radius of 2 meters, then the area of mirror A is 1 times pi times 1 squared, which is just pi square meters. That's what that M2 means. While the area of the other one is pi times 2 meters squared, which is 4 meters squared, so it's 4 pi. So one has an area of pi and the other one has an area of 4 pi. So if I have twice the radius you have, that means I have 4 times the area. It's like what we were talking about with the flux, where it depended on the temperature to the 4th power, right? The area of a circle depends on the radius to the 2nd power, and so something that's twice as big has 4 times the area. And so that's an important criteria in telescopes. You want as much light as possible to come in. Bigger is better when you're talking about the diameter of your telescope. When people talk about the size of a telescope, they're never talking about the length. They're always talking about the diameter. And so I'm just saying, if you're 3 times larger in radius, you have 9 times the area, and so on. So besides light gathering power, the other important property is angular resolution. And this is the thing, if you're driving down the road at night and you see a car coming towards you from far away, it looks like a single light. It might be a motorcycle. But as it gets closer, that single light splits into 2. Your ability to separate things like that is called the angular resolution of your optical device. When you're looking through your eyes, it's just your eye. But angular resolution for a telescope is its ability to distinguish 2 points that are very close together. And that depends first on the diameter, but also on just how well made the lens, how smooth the shape is as compared to what it's exactly supposed to be. For example, the Hubble Space Telescope, if it were blown up to be the size of the United States, if it were just scaled up, would have no hills or valleys in it higher than 2 inches. It's super duper smooth, and it's very close to matching the exact mathematical shape it's supposed to match to give the highest image quality possible. So that's a little bit about light gathering power, angular resolution, and the objective lens or mirror and the eyepiece. Let me go back to the pictures here for a second. Did I lose that? No, there it is. Okay, so let me come over here, page down. So this is a picture of a lens that's gathering light and bringing it to focus. That's what lenses do. These are the 2 basic types of telescopes. The one on the left is called a refracting telescope, and it's called refracting because when light goes through glass or water or anything clear, it bends, and that bending of light is called refraction. So this is a refracting telescope because it's using lenses. This is a reflecting telescope because its main optical component is a mirror. Sometimes these are called Newtonian telescopes because he was the first one to build one. So you can sort of see how this works. In the refracting telescope here on the left, light comes in through the objective lens, and then it goes down here through the eyepiece and gets focused to your eye, right? It's a little different in a reflecting telescope. The light hits a mirror. In the back, this is the objective mirror because it first receives the light from the object. And then that light is focused up to a little mirror called a diagonal mirror, or a secondary mirror sometimes. And then it's focused out, it's reflected out the eyepiece to the side. Here's the eyepiece here, and then that's where your eye looks. And so the one on the right is a reflecting telescope, the one on the left is a refracting telescope, and there are different flavors of each. I just had a few more pictures. So here is a refracting telescope, which uses lenses. That's what Marvin the Martian looks through. Here's a typical reflecting telescope, sort of with the stuff drawn there so you can see it drawn on top of it. So the rays come in from something far away. The rays are typically parallel. They reflect off the mirror in the back. They reflect off the secondary mirror, the diagonal mirror, and they go out through the eyepiece. Here is a variety of reflecting telescopes. This is called prime focus. Notice there's no eyepiece in this one. You might just have a CCD up here, some kind of digital camera that's just recording the image, and then it's fed out through a wire to a computer or something like that. Here's an observational telescope like we just saw in the last one. And this is a slightly different variation. This is called a Cassegrain. Instead of reflecting the light out the side, it's reflected back down through a hole in the objective, and your eyepiece would be out here in the back. And so the Swasu Observatory has a Cassegrain, sometimes called a Schmidt-Cassegrain telescope that looks like that. So you can see this is a mirror from the primary mirror, or the objective mirror of the European Southern Observatory's very large telescope named Yeppen, just after it was recoated with aluminum. The mirror is a little over 8 meters in diameter, which is like 25 feet in diameter. You can see the man standing here next to it. Right, here's the man. Notice it has a hole in the center. That's where the information goes out through either the eyepiece. Usually, those really big telescopes just have CCDs back there and computers that store the images. Here are a few really big telescopes, and you can usually see people in these images. Here's a person down here in image A, right, and there's the telescope. We have really big telescopes to take, do all kinds of images of very distant objects. The one on the right is a Palomar 5-meter reflector, and the Gemini 8-meter telescope is on the left. Good Lord, those are big, aren't they? This is a 10-meter Keck. Notice it's composed of 36 hexagonal mirrors that are all been put together. The James Webb is like that also. They're just a whole bunch of smaller mirrors that are stuck together and match each other perfectly. So a few more things about telescopes. Describe what we mean by angular resolution. Again, I kind of said that a little while ago. It's how crisp your image is. It's the ability of your instrument, whether it's a telescope or a magnifying glass, a pair of binoculars, or something, to distinguish two distinct points of light from each other when they're close together. Describe the properties of a telescope that influence angular resolution. We already talked about that. It's diameter of the objective, if it's a mirror for a reflecting telescope, or a lens for a refracting telescope, and the quality of the surface. And finally, how do the eyepiece and the objective work together? So the objective creates an image. The main optical element in a telescope, the objective, creates an image, and the eyepiece magnifies it. And that's a really important distinction, because you can't get a better eyepiece and make your image any better than was created by your objective. If you had a bad objective in your telescope, it doesn't matter how good your eyepiece is, you won't get a clearer image, because your image ultimately depends on how good the objective is. So you don't want really great eyepieces with a really bad objective. You want them. You want your eyepieces to be about as good as your objective is in terms of their optical quality. So you're not magnifying something that's bad. It's also true that magnification isn't always a big deal, as you've seen with images. Let me pull up these other images we were looking at a minute ago. So if I scan up here, go to the top. So let's look at that center image, right? And if I magnify that, let me just zoom in like 400%. Say okay. You can see that blowing that up any more than that isn't going to improve the image any. That I'm limited by the quality of the image that was on my computer to begin with. And that's kind of the way objectives and eyepieces work. The objective lens gives me an image that has a limited quality to it. It may be really good, it may be okay, but using an eyepiece to just blow it up bigger and bigger isn't going to make it any crisper. And so that's the relationship between those two. Now let me zoom back out here. I think I was at 100% maybe. So this section is on telescopes of today. We're building enormous telescopes. I think that's the most important thing out of this first section. Visible light and infrared telescopes can be really big. We get a little bit of infrared at the surface, and so we can see some. We can use some infrared telescopes at the surface of the Earth. Not very much, though. Mostly are visible light telescopes or radio telescopes. But you can see these are 100 feet in diameter. A 30-meter telescope, that's about 100 feet. That's in Hawaii. There's a 39-meter European extremely large telescope. The giant Magellan at Las Campanas is 25 meters. So we're building enormous telescopes. We'll come back to those in a little bit. Discuss the factors around choosing a site for a telescope. So when you're building a telescope, you want to have cloudless days. You want to have not much light pollution, so you don't want to be in a city or even near a city. You want to have steady air, not unsteady air. Unsteady air is, think of throwing confetti. It just messes up the air, and so you don't want to have that. And you want to have a high elevation to get above the weather and things like that. And so usually telescopes are in remote areas on mountaintops. And so that's why you see things like Mauna Kea and these other ones that are in mountains, because that gives you the best opportunity to have clear air, steady skies, no light pollution, and cloudless days. That's what you're trying to do there. The higher you are, of course, the more air you're above in the atmosphere, and so the closer you are to space, and that helps too. This next section, called adaptive optics, is about what to do. Some clever science that's being done to improve the images when the air is not steady. And this is a very cool technological trick where they can actually adjust the shape of the telescope to correct for unsteadiness in the air, which almost seems impossible. But what they do is they use a laser and shoot it out in the direction the telescope is looking, and some of that laser light hits the air and bounces back into the telescope, and that tells the telescope, since the telescope knows what the laser has and knows what its image should look like, when it looks different, the telescope can correct that. And so it can constantly be correcting its shape to correct for the unsteadiness in the air and get even better images. There are a few really cool tricks like that that have been done. So that's adaptive optics. That's what that's called, adaptive optics. So visible light detectors. So this is what I was talking about earlier. These are CCDs, charge-coupled devices. Back in the old days, we used film. These are the two basic things you can do to store your images or your information. You can use CCDs or you can use film. CCDs, they're just dramatically improving over the last, every year they're better than they were the year before. And so we're getting astonishingly good images now. They're much more sensitive to light than film. Film typically has had higher resolution. That is to say, its pixel size has been smaller than on a CCD, but even that's changing. And so there's almost no reason to use film anymore, at least for astronomical reasons. A spectrometer, we've already talked about that. That's the diffraction gratings that we used in the last chapter to break light up. It acts like a prism. They're just prism, diffraction grating, and spectrometer are really all sort of names for the same general thing, where you're taking the light and you're breaking it up by its wavelength or frequency, either one. Okay, let's talk just a little bit about other wavelengths. So we've looked at visible light primarily, that's what we've been talking about, but there are also telescopes for other bands, radio telescopes, X-ray telescopes, ultraviolet telescopes. Radio waves have much longer wavelengths, and so that's the challenge for them, and that's why you'll see, like if you see a radio telescope in a science fiction movie, or just in a science movie, or a science documentary, or in a book, they look like enormous dishes. Sometimes they'll be 100 meters in diameter, or 30 or 40 meters in diameter. The point is, in order to get good angular resolution image sharpness, you want to have an objective that's large compared to the wavelength of light that you're capturing. With visible light, that's pretty easy to do because the wavelength of visible light is, measured in billionths of a meter. But radio waves can be in meters or more, and so we need very large dishes. And so one thing we can do is use this process called interferometry, where you take a whole bunch of dishes, a whole bunch of radio telescopes, and wire them together and make them act like they're one giant one. So let me see if I can pull up this picture here. So I may just go back a little bit. So F3. So these are just some telescopes on mountains. This is one of the clearest pictures of Jupiter ever taken. This is using adaptive optics from Earth. It's a shockingly good image of Jupiter. These are CCDs. This is a picture of somebody on the left with a visible telescope and on the right with an infrared telescope. You can see that the plastic bag does not do a very good job stopping the infrared. The infrared kind of sees that plastic bag is transparent, even though it's not transparent to visible light. This is a diffraction grating that's put in the optical path of a telescope here. This is a very early radio telescope. This image has been constructed of radio telescope observations from the very large array of the galaxy called Cygnus A. The colors have been added to the eye to help the eye sort out the regions of different radio intensities. The red regions are the most intense, the blue regions are the least. The visible galaxy would be a small dot in the center of the image. The radio image reveals jets expelled of material more than 160,000 light years long on either side of the galaxy. So that's the galaxy in the center. Right, this is taken by a radio telescope. Here's the radio telescope dish. Right, here's an array of them. Right, again, we kind of make all of these act like they're a single telescope. Right, and so they give you a much bigger area. And remember, area is light gathering power. And so if you can make them act like a single telescope, you get much better resolution and much more light. And finally, you can have telescopes around the globe all working using interferometry to create a single image. It's different from just taking two images with separate telescopes and stacking them on top of each other somehow. Here you're actually having all of these act like a single telescope. They're all talking to each other in real time. This is the giant dish at Arecibo, which is now gone. It got destroyed in the hurricanes, I believe. They just finally let it go. But that dish right there in the center, they couldn't turn it, but it was always looking just straight up. But they took a lot of beautiful data with that. So let me switch back here. So, space observations. Describe the advantage of making astronomical observations from space. So, if you want clear images, go into space and take your images. Taking images from space eliminates all weather-related factors. You don't have to worry about light pollution, at least not nearly as much. And certain wavelengths, of course, don't penetrate the Earth's atmosphere at all. If we look at this image. This tells us which wavelengths penetrate the Earth's atmosphere. And as you can see, of course, nothing above the near ultraviolet, the ultraviolet that's near the Earth's atmosphere, penetrates. And there's just a little infrared that penetrates, and most of that doesn't. And the long wave, radio waves don't either. And so there's a whole lot that doesn't penetrate. If you want to see these at all, you can only do it with space telescopes. But for any telescope, you get crisper images and much nicer steadiness and things like that. And of course, if you're not looking in the direction of the sun, you can go all day because the atmosphere isn't making the sky bright in the daytime. You can, as long as you're not looking towards the sun in space, the sunlight won't interfere with your observations, even if it's visible from where you are, as long as you're looking in another direction. That, of course, doesn't work during the daytime on Earth because the light scatters the atmosphere in every direction. The atmosphere scatters the light in every direction. I think the last thing we're going to talk about is a little bit about the Hubble. Most important scientific in the history of mankind. It's insanely smooth, the Hubble Deep Field. And so I'll try to get a picture of the Hubble Deep Field. You can Google that. I may make that a class activity, Googling the Hubble Deep Field. The Hubble telescope spent 100 hours taking a picture of an area of the sky the size of a grain of sand at arm's length. And it contains about 10,000 galaxies in it, in that one little image that's the size of a grain of sand. And they were looking for the darkest area of the sky, so they were trying to find a place that had almost no light coming from it that we could see easily. And they still got 10,000 galaxies in it. This is pictures like this is what makes astronomers estimate that there are probably a few 100 billion galaxies in the universe. Let me scroll down a little bit. These are just some of some space-based observatories. So these are just the Chandra Observatory. So there's an X-ray and an X-ray and an X-ray and an infrared and gamma rays and visible light and infrared and visible light. These are all space-based observatories that are either have recently closed or are still active. And so we've got lots of instruments up there taking data. And the nice thing about space is they can last a really long time up there. They're not being eroded by weather. The downside of putting an instrument up there, of course, is that if you have a problem with it, like we did with the Hubble, somebody has to go up in a spaceship and fix it. But they're usually pretty good at making those, avoiding that anymore. All right, that's it for Chapter 6.